Good day to our respected lecturers and fellow classmates. We are from Group 3 and today we are going to present our investigation and experiment on projectile motion. My name is Kwashiong and my metrical number is AA240200.
My name is Lin Chuanjie and my matrix number is AA240738.
My name is Kang Yi-hong and my metric number is AA241115.
Hello guys, my name is Ang Zhenming. You guys can call me Ang, and my matrix number is AA240025.
Now, let me guide you through our objectives. Number 1, it is to understand and grasp the concept of projectile motion in our day-to-day life. Number 2, it is to analyze the effect of launch angle on range, height, and time of flight. Other than that, it is also to help visualize the parabolic trajectory of a projectile when it is in motion. Number 4, it is to comprehend the role of velocity components in motion, and lastly, it is to compare the theoretical and experimental result. Now, for the introduction. A projectile is an object launched with an initial velocity influenced by gravity and sometimes air drag. Its upward distance is called height, and its horizontal distance is the range. The curved path that it follows is the trajectory. In this mini project, we explore how different launch angles such as 0 degree, 30 degree, and 45 degree affect a projectile's height, range, and trajectory while keeping its initial velocity constant. This helps us better understand two-dimensional motion and the role of initial conditions. Now, I'll walk us through the methodology for our experiment, which is the approach we use for this research. This part of the report explains the method used for collecting and the interpretation of data we measured and calculated throughout the experiment. This ensures the accuracy of the data we gain as a proof of our genuine interest in the concept behind projectile in motion.
Okay, now it's my turn. Today I'm going to talk about the apparatus. First, we use the rear tap measurer to measure the distance between the launch point from the launcher to the edge of the paper. Second, we use the safety glasses to protect the eyes from potentially uncounted flying projectiles. Third, we use a long ruler to measure the length from the edge of the paper to the landing marks on the plain paper. And next, we use the pen to mark and group the mark landing points on the plain paper. Fifth, we use the ruler by placing it perpendicularly to the side of the long ruler. Measurements for the distance of the landing points can be more accurate. Six, we use the scissors to cut the tap into the proper length. And seven, we use the tap to tap the carbon paper on the plain paper to secure it from flying away. And eight, we use the mesh hanger as a guide for making sure the launcher is consistently aligned with the original configuration. We use carbon paper to mark the plain paper upon the projectile lands on it, and 10, we use the plain paper allows the carbon paper to leave markings on it after the projectile lands on it. And 11, we use the plastic tube by pushing the projectile into the projectile launcher. And 12, we use the mounting panel for attaching and securing the launcher onto the tabber. And for the last two is also important. We use the projectile launcher as a protector, and a plumb bob setup is attached which allows for precise. And last, we use the smartphone to record the whole process as proof and demonstration. And smartphone we use calculate the time when the experiment is conducting. So I'm going to continue about the procedure. The first step is about a mesh hanger was tapped onto the table vertically while slightly touching the projectile launcher. And second step is projectile launcher was set horizontally at 0 degree. And third step, while making adjustment, both eyes are aligned onto the protractor and plumb bob to ensure no parallax error. And next is about the height of the launch point given on the projectile launcher was measured. The fifth step is a metal ball was placed onto the projectile launcher and pushed inside using a plastic tube. The sixth step is a distinct two-click sound were confirmed to set the projectile launcher for medium range. And 7 is projectile launcher's string was pulled slowly to fire the projectile to it. Okay, now is the last procedure. So we continue 7 to 8 lah. So now is 8. Paper alongside carbon paper were placed on the estimated landing point of the metal ball. Paper was stacked onto the table and carbon paper was stacked above it. For the ninth step, the distance from the launch point to the edge of the paper was measured and recorded. And for the 10, the projectile launcher was reset to the same setting as step 5 to 6. Next, the metal ball was fired 5 times onto the carbon paper using a constant setting. For the 12th step, tape from the carbon paper was removed to reveal the marking made onto the plain paper. And next, the distance from the edge of the paper to the landing points were measured and recorded into table 4.1. After that, also the last step, step 2 until 13 were repeated for launch angles of 30 degree and 45 degree.
So this is our experimental result for 0 degree, 30 degree and 45 degree launching angle. For the calculations, we start the calculations at 0 degree angles. First, we're using a formula to find the time of flight, and we use the time we calculated. We can find the initial velocity. In this way, we also can find the horizontal velocity and vertical velocity. For the observations, we observe that the ball travels the farthest distance when the launching angle is 45 degrees. This is because the energy was evenly split between vertical and horizontal motions. It allowed the ball to stay in the air longer and travel farther. At 30 degrees, the ball moved forward quickly but didn't stay in the air long. It resulted in a shorter range. For the 0 degree, the trajectory was nearly flat and curved downwards quickly. It shows the minimal flight time and distance. We also observe the shapes of the trajectories varied with angles.
Now we look at the discussion of this project. The experiment was successfully conducted with the data which show a good consistency. The percent errors in range were below 10% at all angles, which indicate the close alignment with the theoretical predictions. Some minor deviation occur due to the real-world factors like slight variation in nudging, human error in marking impact point, and other environmental influence such as the air currents or the uneven surface. While the effort were made to reduce uncertainty, such as using a similar size paper or some variability was inevitable. Still, the overall trend supports the theory, especially with the maximum range observed at 45 degrees. In conclusion, this mini project aimed to explore how launch angle affect the projectile motion. Through the testing at 0 degree, 30 degree, and 45 degree, we observed that changes in angle are significantly impact the flight time, maximum height, and horizontal range. The 45 launch produced the highest peak, which is 0.581 meter, the longest time of flight, which is 0.63 seconds, and the greatest range, 1.75 meter.